This is a report of Lab 1 observing the constant velocity of a moving object. The goal for this experiment was to use Newton's laws of motion and apply it to real-world scenarios to better understand the behavior of objects interacting with their surroundings. While looking at the constant velocity of an object, we applied Newton's first law of motion, stating that if an object is at rest or is moving at a constant speed in a straight line, it will remain at rest or keep moving at a constant speed unless acted upon by a force. For Lab 1, we analyzed the cart moving on a straight track, traveling at a constant velocity. If we consider the formula for net force is equal to mass times acceleration, meaning that if there is no acceleration, the net force is zero. In this video, it shows the cart being pushed across the track. To get the average velocity of the object, I recorded the movement of the cart by plotting points using the axes to find the object's position and corresponding time used to find the average velocity. For this, we must assume that there is no external forces on the system. Thus, no external forces are acting on the cart, and the net force will be zero, resulting in a constant velocity. Tracker then outputs a graph of position versus time, showing a constant change and representing the velocity of the system interacting with its surroundings. Since the cart is moving to the left, it is moving in the negative direction as depicted by the graph. The following data was taken from Tracker to form a computational model and to calculate the average velocity. The velocity is negative, since the object is considered to be moving in the negative direction. In this experiment, we can disregard the mass since there is no acceleration. The position vector is set according to the axes I set for the cart. We then use the initial position along with the final position and time to calculate the velocity vector. To represent the cart's motion over time, a loop will be set to the time period with which we recorded the position change of the cart. The net force is zero since there is no net force, derived from the velocity update formula of Newton's second law. The position of the cart is then updated by adding velocity times delta t. If we run this code, we see that it outputs a similar position versus time graph to the one in Tracker that represents the experiment. We also see the velocity versus time graph, representing zero acceleration over time. If we look at the graph comparing our experiment to the model, the lines are almost identical, both showing the output of our calculations. We see that the line for GlowScript model is straighter as the loop causes more consistent calculations and does not consider the effects of external forces. If we were to change the orientation of the axes, we see that the direction of the velocity changes. This is because the slope of the graph determines the direction of the object. In this instant, the cart was moving to the negative direction in the experiment. Therefore, the axis represents the direction of displacement of the cart. Ultimately, this means that the net force of the system is zero. Consider friction and gravitational forces. It is difficult to determine how many pushes or pulls acted on the system. Since we observed the cart moving along the horizontal plane, we only consider horizontal forces for the velocity, and vertical forces such as gravity would not have an effect. We can conclude that these forces did not affect the constant motion of the system, and therefore the system remained traveling at a constant velocity.